questions, so please do that if you have any. Then I wish you good luck.
Thank you. Before starting, if you guys can't hear us, just like keep doing this so that we can fix our mics, okay? Thanks. So, how many people in the world do you think suffer simultaneously from heart and kidney disease? Well, it's actually 9%. This is because heart-related issues are linked in a vicious cycle to kidney health. Creatinine is one very important molecule. It is created in the muscle and then filtered out by the kidneys. But when found in large quantities in the blood, that may indicate bad kidney filtration. We created NephroPal, a sensing device that provides continuous monitoring of creatinine with a potential to become wearable.
But what makes NephroPal special? We use an enzymatic bioassay that converts creatinine into ammonium ions, and it is those ions that are then detected by our ISFET. Now, bear with me. ISFET actually stands for Ion Sensitive Field Effect Transistor. And its signal is then sent via Bluetooth Low Energy to our user-friendly app. And it is on the app that the data is processed and visualized. Thanks. So, for the enzymatic bioassay, there are actually already solutions available on the market, but they use 3 different enzymes. We use only one, creatinine deaminase. The result, a 1-to-1 conversion of creatinine into ammonia. But wait, in the physiological pH, the ammonia is actually transformed from ammonia into ammonium ions, and that is what we can detect. Our sensing technology is also based on miniaturization, as we aim to make the sensor wearable for the future. That's why we use 2 already small components. First, we use a carbon screen printed electrode as our helper component because it already contains an integrated reference electrode, and we use its surface to immobilize the enzyme. Then, as our sensing component, we use an ISFET, or as I said before, ion sensitive field effect transistor. And its surface is covered with an ammonium ion selective membrane, so that these ions can actually be detected. Now, the medium in which we want to measure it is actually quite complex, which is why we need to take into account the pre-existing ions of ammonium, but also other ions that might cause an interference. That is why we designed a differential ISFET system, which means that in the flow, we place one ISFET before, so over there, and one after the reaction takes place. Here's what the actual microfluidic setup looks like. Oh, it was a video.
So, the readout portion of our system is quite straightforward and only requires a cell phone. Within the ISFET interface, the outputted voltage is linearly dependent on the logarithmic of the concentration of the targeted ions. Then, the microcontroller and the ISFET communicate together and send the data to the app via Bluetooth. Bluetooth Low Energy. For the app, I think it's best we show you. So, our app, let's play it. Our app is user-friendly and shows user information and is capable of creating personalized calibrated curves and also saving and visualizing data. The app will in the future be able to send updates to its users and pave the way for a more personalized treatment. Now, the advantage of our device lies in the continuous improvements we plan on implementing. For a wearable future, NephroPal is set to miniaturize our current microfluidics and make it into microneedles as a patch. Also, since our device is already small, we can add other ISFETs with different ion-selective membranes to allow for the monitoring of different ions or different molecules. And like this, we can have, for example, potassium. And like this, we have a more generalized system. We would like to thank all of our advisors here for helping us reach for the skies, and we would like to thank you for listening to our presentation, and we invite all our members to help us answer the questions. Thank you.
Right. Please take the stage. Are there already any questions from the jury?
Thank you for your nice presentation. So I did not see that much about how you integrated the whole system. So I mean a picture of the whole device and how you just integrated all of them. If you have done that, would you please explain a little bit?
Okay, so for the competition, we used a pump through which the fluid flows, and it goes through the microfluidic system that we depict here. There was supposed to be a video, but I think it didn't play, so I'll just play it to show you how it's set up. And these are linked. So for the competition, we measured it with the computer because it was easier for us. But in the future, we would use the app that we already started developing. Yeah.
And also, like, the microcontroller is linked to the ISFET. So basically, we need a reference for the ISFET to work. So that's why you use the string SPE. And also here, you can see it's made of resin. So actually, it's really that small. And the pump was just so that we would have automatization, so with the inlet and the outlet. And actually, we had made sure that the volume that is in there is below the 100 microliter that we were given, so that we will have really a sequential of samples, so one replaced the other. So we have a continuous then.
Okay, and thank you very much for such a nice talk and great work. I have a question regarding the sensor itself, how that works. Because you mentioned that you have an enzyme producing ammonia that converts into ammonium, and then you said something like there is ion selective or some selective membrane that transports this ammonium ion specifically. Like there's nothing else going through? Or is it really in your system, or you plan to integrate that?
So I can answer all that. So basically the ISFET has on the gate ion selective membrane, so the ammonium one, so only normally the NH4 plus ion goes through, but actually we know that potassium is an interferon, so that's why we decided to go for differential. But the membrane is made of ionophore that are charge specific and size specific. So,
okay.
Yeah.
And so coming back to what just showed in the slide. So at this moment, you have the reaction chamber separated from your ISFET sensor. That these are positioned somewhere else. And this ISFET sensor, does it still contain this ionophore providing the selectivity? Or
Yes.
this? Oh, thank you.
So I also have a question about this, exactly that. So I'm an old ISFET guy, so I do that for many years. An ISFET needs a reference electrode
Yes.
to work stably.
Yes.
So where is your reference system?
So what we did is basically we isolated the grounds, right? So when you have common grounds between the two, the differential measurement doesn't work.
Okay.
So actually we use one reference, and that's the common ground, or like the common reference voltage between the two. So what happens is, if the reference voltage for this ISFET goes up, actually those voltages drop down and are referenced to the middle. So yeah, does that answer your question?
That's answering my question, yes. And you know, these two ISFETs, these two red slides here, these are the ISFET chips.
Yeah,
and
exactly.
These are commercial ones you use, so they, you are sure that they are identical and so on. So because you know, if working for reference, they should be electronically similar, right?
I mean, the most part we could also do it in signal processing afterwards, right? So even if they weren't identical, even if they were homemade, we would still be able to do the measurements and get a difference in the signal, right? I mean, we calibrate the sensor always, right? So in the signal processing, we would calibrate the sensor to the baseline, which is independent of their difference. So,
and the two ISFETs, so one works then as a sensing ISFET, the other one works as a reference FET?
Yeah, basically, this one is just to take away the common mode. Yeah. So the common mode being like common potassium, common, whatever is in the blood, in whatever, right?
Okay. So that's the ISFET, RefRet concept out of the 80s. Yeah, so that's quite there for a while in the field. Yeah, but I think it's a big challenge to have the reference FET not sensitive to the analyte. So it needs to be a clear reference. How did you tackle that? So the surface chemistry of the two IS FETs, what's the difference?
Yeah, so basically the enzyme is in there. So
enzyme is on the reference electrode then, on this SPE.
Yeah, exactly. Yeah.
What is the difference between the two transistors then?
Well, one, if you look at the, can we move to the other microfluidic slide? So if it comes in here, the fluid, we will measure the fluid without anything.
Okay.
Without anything. Then it goes above the SPE, where the reference is. So the reference is, it references both. The enzyme is placed on here, I think with hydrogel, if I'm not wrong, or maybe we change that after the after the report, and then it moves on and goes to the ISFET, where the ISFET measures the NH4. So thanks to the microfluidics, the NH4 doesn't move here. It goes with the flow and goes to the second ISFET. So that's what we measure.
Did you see differences in the flow rate? So if you have different flow rates, you have a different readout?
Oh, yeah.
Yeah, so basically we had our microfluidics guy who tested with different flow rates, and then ultimately the decision was a mix between what would give us the best measurements, the best difference between concentration measurements, as well as what we needed for the competition was that 5-minute window. So we tried to make a balance between both to get to the right flow rate.
Okay, we can talk offline later on.
Very good, thank you. I mean, I was going to pick up on the enzyme question. Most of these devices are continuous, and so they're aimed for continuous, and so they have to last long.
Yes.
And binding enzymes on surfaces takes a lot of effort, especially for it to last. So, what's your point on that?
Okay, so just the design slightly changed because we noticed that our enzymes were actually dying. And so we trapped the enzymes in hydrogel so that they would stay moist and survive longer. And we tested that later on after a day to see whether they were still functioning and active. And we trapped that by making a little bit more of a well to have the space for it.
I mean, if I can add on that, actually we did the hydrogel, I think it was on Friday, and travel with it, and it was still working perfectly fine for the competition. So fantastic. It passed the test.
Well done, very well done. I can have a final one. It's on the, you want to make this smaller.
Yes. Because
you want it to be more usable. When things get small, fluidics don't work the same anymore. Well, have you thought about that a little bit?
Yeah, so basically we actually had a small talk about the microneedles. And for example, there is a startup at EPFL that is working basically on that. So using microneedles to basically have the ICF coming out, because blood it's easy, but ICF it's not. And it was promising, so we hope in the future to partner with them and tackle that.
I also think that the most scalability is also on the side of the electronics, for example, where we could definitely, like making a patch. I think if you saw the size of the microfluidic, which is that part, I mean, already a sensor that big, it's already kind of wearable, right? And the electronics is definitely addable to as much as a small device, right? So, yeah. So currently, the electronics we're using is that one. Is just to be reliable, to have like a standardized thing. We also have PCBs that we made, but due to delays in the chips ordering, we just went custom way with things that exist already. So yeah.
All right. I think your answers were answered properly. So now we can move on. I want one round of applause again for.
Thank you.
All right.
Can you give this to you?
Yep.
Thank you.
Yeah, you can leave it on the table.
Tell them about the laser exhaust.
Yeah. All right. Let's wait until things settle down.
I can stand on this side. You want to stand on this side? Okay.
Here we'll have a clicker, and this is also a laser pointer if you want to.
Wonderful, thank you. Yep.
All right. Good luck, SensNC.
Thank you.
Hi, everyone. My name is Bella.
My name is Rohan.
And we are SensNC from Raleigh, North Carolina. We're super excited to share the innovation behind our biosensor with you today. So the task of the SensUs competition this year was to create a continuous monitoring system for creatinine levels to tackle the problem of continuity, which is very difficult in sensing, as we've heard all about during the symposium this week. We decided to use a multiple electrode system. One electrode system includes copper deposition on the surface of our electrode, and we're using copper as a non-biological recognition element for our sensor. So the copper is released from the electrode surface of one system, and the other system senses. So after the copper is released, the copper ions will form a complex in the solution with the creatinine. This is a copper creatinine complex pictured on the screen. It has a 2-to-1 ratio of creatinine to copper. The copper binds to the endocyclic nitrogen on the creatinine, forming this complex as long as there is water in the solution as a competitive inhibitor. And our other electrode will then use cyclic voltammetry to measure the oxidation and reduction peaks of the solution. So the peaks pictured here, A and B, are the oxidative peaks of just copper in a solution, and then a peak specific to copper with creatinine. Using these peaks, we find the difference in the voltage to draw a calibration curve that we use in our sensor. The estimated range of detection is 30 to 300 micromolar with a correlation coefficient in DI water in our initial tests of 0.9707, which we found very promising. We chose to use a non-biological recognition element as the basis of our design because of the shelf stability and ease of transport. A lot of biological recognition elements such as enzymes or antibodies are required to be kept at certain temperatures or are just difficult to transport. So using a non-biological recognition element, copper, is very easy to transport and keep stable. It also reduces the risk of degradation because copper will not degrade in the same manner that enzymes do. It's cheaper. We estimate that it can cost up to 75 times less to produce with copper because we're just using copper sulfate in the current production, and long-lasting.
Introducing Q-Test. This is our wearable device that uses microneedles as a way to painlessly extract interstitial fluid from outside the body. Here we have a diagram of our device. We have the electronics, the electrodes in the sensor, and the microneedle patch. This is all covered up by an enclosure, and it is worn on the outside of the body using a medical adhesive. All the data that is collected by the device is sent to an app, which the user can use to track and analyze their creatinine levels as needed. Here's what it would look like if someone is wearing it on their arm while exercising. And ideally, we would like to get the device down to that size compared next to a penny. And we know we can do this due to the size of our potentiostat module. It is 11 millimeters by 11 millimeters. Our lab specializes in making microelectronic devices. We have castellated pinouts on the PCB. We have a DAC and ADC to control the voltage output sent to the electrode, as well as the output voltage that is turned into the digital signal. These also work with a reference voltage, a potentiostat, and a transimpedance amplifier. We can get results every 3 hours with our device. The low sample frequency allows for longer lasting electronic and device lifetimes, and these can be swapped out very easily using, due to the nature of our microneedle design. Microneedles are very painless, and this combined with the lightweight and small design of our device leads to easy and painless application. And once again, this highlights that our device is portable, reusable, rapid, and continuous.
Thank you so much for listening. Are there any questions?
Who of the jury members has a question?
Yeah, hi. Thank you very much. I found a question on the repeatability. How does it actually work? So do you flow something out? Does it recover? Or?
Yes. So our plan right now, our current device obviously does not look like this. We were not able to develop a wearable biosensor in a couple of months. But our plan is to use microfluidics to transfer the fluid obtained from the microneedles, the interstitial fluid, to our sensing units, our electrodes, and then that can connect to the PCBs.
But is that then connected to your arm as well, or?
So because we're plating copper on our electrodes, the copper and the electrodes will not come in contact with the body at all. We'll use the microneedles as a way to draw up the fluid and then draw the fluid away from the skin where the electrodes will be.
Okay, so then 2 devices, I guess, or?
Yes, sort of. So the end proposal of using the microneedles is what we'd imagine the further applications would be. We haven't developed the system with the microneedles and the microfluidics to get the ISF to our sensor, but we have developed the sensor and the electronics portion.
Okay, thank you.
Sorry, just to continue, I understand how things go to the sensor, how things go away from the sensor.
Do you want?
Yeah, so we obviously recognize that copper is not something you want to leave in contact with the body. So our current plan right now is our first target population is actually kidney transplant patients, because it was very easy for us to, it was very easy for us to focus in on that population because we had connections to a university that actually specializes in that. And so these kidney transplant patients will have to go back to the doctor pretty frequently still. So our plan right now is to have a storage compartment within that device. And because we're drawing up such a small sample size, we'll be able to leave the used samples within a storage compartment in our device. And when the patient goes back to the doctor, they can turn that in for proper disposal.
Okay, so question from my side. So you're one of the few teams using a synthetic receptor concept. Yeah? So it's only a few, typically the biological receptors are used. And with all these approaches with synthetic receptors, the selectivity is always the biggest topic. How is it that your surface is selective to creatinine and to nothing else?
So we did actually come into issues with that within our testing. So obviously our best concentration curve that we have up here, just for ease of understanding, was done in DI water. So the only option the copper had was the creatinine.
Exactly.
Yeah, when we started working in interstitial skin fluid or just in PBS, we did notice that it does produce precipitants with some of the salts in there. But because we can deposit an excess of copper on the electrodes, when we release copper, there's enough to bond with those salts and still with the creatinine. And as we got further into our testing, we were able to distinguish between, we were able to still focus on just the creatinine concentration by focusing at the voltage that the peaks occur at rather than the current. Because those salts tend to change the current values rather than the potential values. And so we were still able to get a fairly consistent result that way.
Yeah, so working in DI water, fine, yeah, and then the next step, and
Yes.
then once you are in ISF, there's all kinds of things. So this curve will have many peaks. Yeah? So what's your concept to really, detect the creatinine, nothing else, which is in the blood or in the ISF?
I can keep going. Yeah. So we did run tests in ISF before competition, obviously, and we still saw only those 2 main peaks forming from the copper and from the creatinine. And because we only saw those 2 main peaks and we focused it on those potentials, we used instead, or what we've started to develop is more of a self-referential method where we notice changes between samples rather than just detecting a sample from scratch. And that ended up being more accurate than doing sample from scratch because you do have those interfering agents in there. But we were very happy when we started running an ISF that there were still only those 2 main peaks within our CVs.
Additionally, we are obviously not finished with the R&D of the sensor, so we're open to more methods. As it gets used in more clinical testing scenarios, we may notice some things that we didn't notice at all when testing in PBS or simulated ISF. So we're still playing around with ideas of maybe adding a membrane in our microfluidics channel to really isolate the creatinine and see we still have some work to do, definitely. Thank you for your question.
Thank you very much for your presentation. It was really nice. I have a question regarding the actual mechanism, how that works. So you have an electrode, there is copper, you just apply some potential, the copper dissolves. But there has to be some counter electrode somewhere. What is happening on that one?
So we used pine electrodes that were made, sorry, I keep skipping too far. We used pine electrodes that were pre-made and commercially made, thank you. And they have a counter and a working counter, working and reference all on the same sort of electrode. And it's a carbon electrode, so we have our carbon counter, and then the reference is silver chloride. And it is all contained within one section, and our microfluidics channel causes the sample to be in contact with all of those.
And I assume the copper dissolves on one electrode. What electrochemical reaction takes place on the other one?
That's so when you run that, so we run the CV to see the electrode release from the oxidation of the copper on its own versus the copper in complexes with creatinine. So that's what that second electrode is doing. The first electrode is kind of just the storage for the copper. So we use that and apply only a voltage to kick that copper off, dissolve it in solution, and then once it's in solution, the other carbon electrode actually produces the CV just from having the chemistry happening at the surface of the carbon electrode.
Really? Because, you have to have a closed circuit. I mean, like if there is, current going through the electrode-electrolyte interface on one side of the circuit, there has to be something going on the other electrode. Because you would be just, pumping copper ions into the solution, there has to be some counter ions, if you understand what I mean. It's in DC field, I believe. DC electric field.
Okay.
Maybe.
So currently the sensor that we used in the testing day only used one electrode because we changed our pitch closer to this time, so we weren't able to have both electrodes when we brought them over. So right now it just uses the mechanical stripping of the copper off of the surface from the flow of our flow cell to release the copper into the solution. So we don't currently have the two electrodes in one system working currently. But that is our plan to develop that and continue researching how we could use multiple electrodes to control the amount of copper.
Okay. The reason I was asking is that, when we apply some voltage, DC voltage, very often you will start splitting water, generating bubbles, and bubbles are, a huge enemy to everything. Thank you.
We did start running tests with both electrodes, and it did show that we were still getting a trend with creatinine concentration changes when doing that two electrode system. So I wasn't entirely sure what you meant by the counter ions, but we have seen promising results having the two electrode system running.
Okay, can I ask you briefly repeat which electrochemical transduction did you use?
Cyclic voltammetry. Or is that?
Okay.
Is that right?
Yeah.
So I think we tortured you quite a bit with our questions. So I would like to ask an open question. So we are in the innovation pitch. So what do you think is the biggest innovation you did as a team?
So the one that we were the most excited about was using a non-biological agent because it is much easier to work with in the lab to be working with copper sulfate than enzymes. We've heard some horror stories from some of our new friends here about how difficult it is to get antibodies to stay stable, to keep enzymes alive, and eliminating that from our process we were proud of that idea. As well as making the sensor wearable. Our lab also specializes in the production of microneedles, so we're not quite sure where we are yet with that design currently, but that's something that we would really be excited to explore.
I would also like to give a shout out to our electrical team member who couldn't be here today. He's my fellow captain. His pet project was that PCB and shrinking it down as small as he could. You can kind of see in the corner we've got a penny in there for size, but yeah. but you know, but it is very, very small, and he's continuing to work on the project after SensUs, and that has been really impressive just to see how far he can get those electronics developed and just how small we can get it without losing any accuracy in detection.
Thank you very much. All right. You can sense. There you go.
The pointer?
All right. Please settle down. Thank you. I'm going to hand you the mic. Good luck.
Thanks. So, hello everyone. We are Team 2 Consens from TU Darmstadt, and we are very excited today to finally present you our creatine biosensor. Okay, the template is currently not working, but generally we are using electrochemical signal transduction to for our sensor. And therefore, we completely self-made screen-printed electrodes by ourselves as a team. And in a standard 3-electrode setup, we're having a counter and working electrode made of gold, and the reference electrode composed of silver chloride. Generally, as a molecular recognition unit functions a single-stranded DNA aptamer, which specifically recognizes and binds the creatine molecules. And additionally, to prevent further unspecific binding, we are using or immobilizing a well-established blocking reagent. So generally, we were able to develop a sensor which is suitable for the continuous measurement of creatinine. Here, for doing a short heating period, the aptamer structure will denaturate and leading to the release of the creatinine molecules, while the cooling down will kind of regenerate the aptamer structure and allowing for a renewed measurement cycle. So our sensor is not only regenerable in this sense, but also that the aptamer itself is highly sensitive and selective, as well as suitable for the long-time storage. So far, additionally, we also integrated a microfluidic system to complete our sensor. Herefore, a pump which is integrated will allow for the continuous flow measurement, kind of paving the way for the real-time monitoring and future applications. And additionally, the temperature control element underneath the electrode will allow for an on-demand regeneration. Now we will move on and talk about how our biosensor is not only capable of monitoring, but also able to adapt to your unique physiology. For this, the crucial step is data processing and data analysis. So we want to tackle the challenges of measurement conditions, ion drift, and baseline, as well as regeneration issues by aiming for robustness and accuracy by maximizing reproducibility and minimizing mistakes and errors. Our concept, which relies on a machine learning model, uses our electrochemical impedance spectroscopy measurement data and feeds it into this model. We chose this kind of model for the adaptability and the variability inside of a sensor, but also across several sensors. But this is not where vision stops. It also goes further than this, where we want to leverage the large data sets and feed it back into the model. This makes our sensor smarter and also robuster. Our vision can be seen in our graphical user interface, which doesn't only show the real-time data monitoring, but also highlights trends. It allows for EGFR calculation as well as personalized entries. Also, there's a notes section which can be seen as a prototype for a communication tool or a health report which can be sent to the clinics afterwards. So our sensor combines many components such as regeneration, automation, and personalized data processing. Our sensor is also sustainable and cost-efficient due to our in-house production. So ultimately, our biosensor is a comprehensive solution which we want to pave the way for a better standard in health monitoring.
on a final remark. Together we can sense the future. Thank you.
Any questions?
All right. Now, I know you're all friends with all the teams here, so I will risk this question in a strange phrasing. We have heard a team this morning saying using temperature in patients is a crazy idea. What's your answer to that?
Yeah, we had that question before. It is a good question, but we don't use a wearable. Our solution is a point-of-care solution, and as we designed the sensor right now, it is not on the patient. It stands on the table. As we imagine it would be on the patient, we could think about minimizing the surface, and of course, we wouldn't have that much heat there. Of course, we could also put there some isolate surfaces or so, but we are right now for this use case, we didn't thought about that it would be necessary to design a wearable.
Very good. If I just push that a little further, in the context of aptamers, actually controlling the temperature is quite important because they need to refold in exactly the same way as they were folded before. And very often you have to spend a lot of time trying to figure out what the rate is and how it goes down. So have you looked into that, and what's the platform?
We looked into that. We really tried to see there's something, and we tried to see, beside all the other challenges, which temperature would be the best for us. But beside ion drift, beside condensation, beside microfluidic flow, beside that many challenges we had, we weren't able to figure out which is the best temperature. But
yeah, I mean, generally, if you come back to like biologically speaking about the aptamers, it's really like individual to an aptamer, which could be like the heating temperature needed for the regeneration. And generally, we can assume as like a DNA aptamer that is like also stable for high temperatures, as it, for example, is applied in the PCR. But yeah, it's under testing which temperature is still suitable. I think firstly we assumed like around the melting temperature, which is also kind of what we found in the papers. And yeah, I think we're still working on this. And also for, if I can complete, for like the cooling down process, there are like different approaches that you can go, for example, cooling down very fastly or like stepwise. And in terms of the competition and the time limit, we are doing it like within 1 minute. Yeah.
Okay, also question from my side. So first of all, nice that you are here, and I also like the pitch. Yeah. So, but for us, it was now 4 minutes to comprehend what you did. Yeah? So maybe you can detail a little bit on these components we see here. So you said you have the screen printed electrode developed on yourself. I see a 3D printed cartridge. I see a flow concept and also an aptamer. So what is done by your team out of that? You did all that? Or?
Yes, so first of all, we printed our electrodes by ourselves. So it was all screen printed by the IDD. Mm-hmm. Then we also did our micro fluidic system by ourselves, also with a 3D printer. Mm-hmm. And we tackled the challenge to write a code to get the microfluidic pump working. And yeah, all in all, the cooling system and also the temperature regulation also went all by ourselves. Yeah.
Okay. And the microfluidic pump is a commercial one, or?
Yeah, we bought it.
Okay. And the aptamer, you found the sequence in a.
Yes, the sequence was published, so we didn't innovate the aptamer itself.
This is also too
no,
much.
that would be not in our time frame.
Yes, sure. Okay, thank you.
Great job, thank you. I have a question regarding how exactly your sensor works. Because you have this aptamer, you have creatinine. What is going to be the change in your signal you are trying to pick up?
Yes, so we tried to see a difference in the impedance. We used electrical impedance spectroscopy, and so we tried to immobilize the working electrode, and there are aptamers on it. They bind to the molecule, and then we should see a difference in the voltage. And so we tried to see also a difference in the impedance. So when there's flowing through a different concentration of creatinine, it should bind more creatinins to our aptamers, and it should change more the voltage. And so it should change our impedance.
But so we were looking at the imaginary part of the Nyquist plot at a specific frequency range.
Okay, and did you see anything? Or I know that it's put very badly, but the reason I'm asking is that I'm looking at the schematic in your TRD, and no matter what step you are at, the aptamer looks exactly the same way, so there is no change in its conformation. So I'm just wondering, how that's related to your sensing.
So the prediction of how the aptamer is folding, it's really hard, and that's a much more investigative part. So we talked to a professional at a university who specializes in aptamers, and her input was that it's probably a small change in the actual, like some graphics show that it's like this. She said probably it's not doing a folding over, more of a changing the sphere itself.
Okay.
So probably the capacity and the size, because of the binding of the creatinine and the difference in folding, that's more of the change we will expect.
Okay, thank you very much.
As I understood, you used EIS to see if you can bind the imaginary part, the phase part of impedance to check. So just I see here it's about 5 kilohertz. So in that regime, you are sensitive to the bulk, let's say. So you are not really surface sensitive. So if you are surface sensitive, you may be blind because of the MCH. So how do you know you're detecting what is binding on the surface and not what is just floating in the medium?
Yeah, that is a good question, because we also weren't really able to say if we have an ion drift there, and because because ice is so sensitive, we weren't facing exactly the change of binding to our aptamer, or is it like just because the ions in the solution is much more higher. We were able to creatinine, and also when we block the complete surface and then do the tests, and to compare to a surface where aptamer immobilized. But of course, there is the big question if we sense the aptamer or we sense many more other ions in there.
Other question. So assume that you are not in a complex medium, you are only in PBS.
Yeah.
So did you test that with MCH? Are you even able to see the conformational change of the aptamers? Or because it's a possibility that with a very thick layer of MCH, that change in aptamer do not affect, cannot be visible by your electrode. Have you tested that?
So you mean that the change of the MCH is blocking the aptamer, or I'm not sure if I understand the question right. But
yeah, I mean the question is, have you tested that if the MCH blocks anything beyond it for you in your regime or not? So in just PBS and different concentration of.
I think I don't understand the question. Jackie? I think I don't understand the question, so maybe somebody else.
I'm also not sure if I understand it correctly, but so I mean MCH is like.
Myself. So when you have an MCH layer on your surface.
Yes.
The MCH is coming after the aptamer.
Yes, but it's shorter. So you have a layer of MCH and your aptamers are floating on top. So it's a chance. So because the numbers are close to that critical, a chance that you just blind your electrode to what is going beyond. So did you have any feasibility tests for that?
I mean, we tested at least the strategies of both immobilizing in
like similar or in different ways. We tried many approaches, like doing it simultaneously, the immobilization, or like after another. We ended up with doing it like after another, but the kind of idea behind this was, of course, to have at least like perfect monolayer of the aptamers, which should then be like at least free for the creatine molecules. And this is where we specifically look at, right, the interaction between the molecules and the aptamer, which should be free and uprightly oriented.
Okay, I will discuss after the session.
Okay.
No, I destroyed it. Okay. Destroying the mic. So I have a question about the reader instrument. So you use a impedance spectrometer, so which one, and any chance to miniaturize later on and integrate?
Yeah, so the reader instrument we used because we used EIS method to get to know if there's any creatinine on it or not. We just took the SensUs, so the SensUs itself from one of our sponsors, and there was a perfectly already GUI which we can put in all our frequencies, all our amplitudes, and all the stuff. So it was quite easy to just focus on all the problems about the aptamer and how to get it onto our surface. Yeah.
Okay, thank you.
No worries.
So,
given the time, an applause for Frequensense. Next up, Team Pulse from KU Leuven.
Are there any other of you, just you? Okay.
How do I use this?
So this is next slide is brief slide, and this is the pointer.
Ah, thank you. Good afternoon to all jury members and team members from all over the world. I hope that you are doing fine and enjoying the beautiful weather here. We are Team Pulse from KU Leuven, and here we are presenting our team sensor, CreaTrack. CreaTrack is a point-of-care continuous creatinine sensor made for AKI patients. For this competition, our prototype consists of a fluidic sensing chamber in a compact package here. CreaTrack uses creatinine deaminase, which is an enzyme that degrades creatinine and generates ammonium ions in aqueous solution as a byproduct. These ions are then detected through an ion-selective membrane made of naphthion, an ammonium selective matrix, and polyaniline, a conductive polymer. Moreover, we also deposit copper nanoparticles to enhance the electron transfer rate between the gold electrode and the membrane. And finally, we use glutaraldehyde linkers to immobilize the enzyme to the membrane. Open circuit potentiometry is used to transduce the enzyme-target interaction. This technique records the voltage between the working electrode and the reference electrode atomic equilibrium, enabling low power consumption while still being reagentless and suitable for continuous sensor. The transduction mechanism relies on the reaction between creatinine and the enzyme, the transport of ammonium ions to the membrane, and the charge accumulation at the gold electrode. As a result, we can measure an increase in electrode potential. Creatinine concentration can then be extracted from a calibration curve, and CreaTrack shows a sensitivity of 90 millivolts per decade and a linear range from 0 to 100 micromolar, making it suitable to detect creatinine levels in physiological samples. The fluidic design consists of two main parts, a sensing chamber and a PDMS tank where you can pipette creatinine samples, and the outlet is connected to a syringe suction pump to operate the flow. We used a commercial reference electrode to provide more reliable and stable potentiometric measurement, which is held within the same inlet by an electrode holder. Continuous sampling is done via sample pipetting followed by fluid suction method. In the first step, the sample is pipetted to the tank, and then it is sucked to fill the chamber where all the measurements are made. In the next step, the next sample is added, and the process repeats. This protocol enables minimal mixing while ensuring no air bubbles form. Continuous potentiometry signal is measured over time, where the fluctuation records the change in creatinine levels. The average values at steady states are calculated and then extracted into creatinine concentration using the calibration curve. CreaTrack is then connected via Bluetooth to CreaView, an app on the phone where you can visualize creatinine levels. CreaView also gives insight into kidney health and suggests diet and lifestyle changes. CreaTrack is a robot's point-of-care cartridge with sensitive bioassay and an user-friendly interface. So CreaTrack is an end-to-end sensor solution for AKI patients. Thank you for listening to our presentation, and we are willing to answer your questions.
Yeah, hi, thank you very much. Can we go maybe to the data slide? You mentioned something about a linear range. Yes. Where?
I'm sorry. I'm using the pointer.
Yes, very
yes,
dim, yeah.
Yes.
But it's there.
Yeah.
No, the pointer's there. The linear range, where's the linear range?
Here. Here it is.
From 0 to 100.
Yes.
It doesn't look linear to me. I mean, those 3 data points.
Well, usually we can...
I mean, you're showing a sigmoidal curve or something, and you're talking about linear range.
You want to answer?
Yeah. So, yeah, I agree that it's not linear here, but it is linear within 0 to 100 microohms, which is more or less your physiological range or above average physiological range. The competition range was around up till 300 microohms, but any sensor after a while it saturates, right? So in the linear range here we can interpret as from 0 to 100 micromolar of creatinine, but yeah, we are just shown it on the entire range that was tested in the competition.
Okay, yeah, but you agree with me that 3 data points is a bit on the low side to infer a linear range here.
Yeah, well, ideally we would test it more to ascertain the limit of detection and like the final exact points between which it is linear. And yes.
Okay, thanks.
Thank you.
Thank you very much for your work. It's a great talk. I question regarding again the principle of sensing. So have you tried like any negative control experiments, like having your electrode, everything, but without the enzyme?
Yes, we did. And actually, in the wearable sensor, we also wanted to integrate two electrodes, one with the enzyme and the other one without the enzyme, as a reference, because it helps also with personalized sensor, because we also have ammonium endogenous ammonium and also interference ions such as potassium. So I think it will be an additional feature that we can add.
And if you compare the signals from these 2 experiments, how do they compare? Like, if you were to plus minus.
It's in the order of a few millivolts, the difference between
But you can still distinguish presence of creatinine from that one. And another question is regarding this Nephion layer. How thick it was?
How thick?
Yeah.
I guess a few, okay, we didn't measure it, but the paper that we referred to, it's around 1.2 or something microns.
1.2 microns. So it was like liquid Nephion.
Yeah, drop casted and then allowed to dry. So the Nephion stays, but the dispersant fluid, it evaporates. And then on top of it, we electrochemically polymerize PANI. So what it actually forms is not 2 distinct layers of PANI and Nephion, but actually a blend polymer of PANI and Nephion.
Okay, so thank you very much for the explanation.
No worries, thank you.
Sorry, I have to go back to the curve that hurts. I mean, in terms of the linear part, it's fine, but how reproducible are these measurements? I mean, there's no error bar on the curve. So what do you think about that?
So there were some issues while we were working on the electrodes. So this is not the final curve that we have. We worked a bit more, but we weren't able to put it in this. But we were able to reproduce it within a certain values. But there are some issues with the stability of the enzyme and stuff, so we plan to work on it later.
So that was my next question.
Yeah.
Because we have to be fair to the other teams, and we asked, the
Yeah.
enzymes die.
Yeah.
Is your enzyme surviving, and why?
Yeah, there are issues with the enzyme stability, but of course, it's not a final thing. But there are no also reported values for turnover number of the enzyme, so we can't exactly infer from the literature how stable it is. So we tested it for a few days, and it seems stable. It's reported that it's stable for a month, but it won't be in actual conditions. So we plan to test it a bit more to test its stability better, and later we can maybe incorporate stabilizers and maybe protein engineer it in a better way so that you have a more stable enzyme finally.
Okay, so I also have a question regarding the chip and the readout concept. Yeah, so I see a screen printed electrode, and you added another reference electrode to it. So why is that, and what are the thoughts to improve further?
So actually, first we try to use a reference electrode on the screen printed electrode, but it doesn't work well because we use potentiometry, where we really need a stable and reliable reference electrode. And in the commercial reference electrode, there would be an inner solution which is separated compared to the sample by a salt bridge, and we cannot do that with a printed reference electrode that is available commercially. So one thing that we would also want to continue working on is to make our own reference electrode on a substrate, and we kind of make separated gel solution. I saw some articles on that, but I know that it might be ambitious, so we didn't do it for the competition, and we try to still use a commercial reference electrode.
So a thin film, solid state, stable reference electrodes, that's a PhD thesis at least. Yeah, so this is something
there are some articles working on that, and we know that it's ambitious, so we decided to stick with the reference for this competition.
Yeah, but could it be that your surface chemistry is kind of modifying the on-chip reference electrode such that it doesn't work anymore?
We tested without and with the reference electrode, and it gives kind of similar readouts if the concentration of creatinine is high enough. So we have that kind of belief that it still works.
Okay.
Yes.
Belief.
Yeah.
we should do research.
We should do more experiments to prove that.
Okay. So I would also be fair and ask you the open question. So what is the, in your view, the main innovation you did? So where are you proud of? So which is the part you did and you innovated?
Yes, so in terms of for the competition, because we want to ensure the most accurate result as possible, so we use the commercial reference electrode, and we still need to make a fluidic chamber, and so the innovation mostly in the design of the chamber with the tank, and also the way that we can form a chamber on the electrode, because it's usually the PDMS is not sticking to the SPE, so we figure out a way. It's like integration, innovation. And also we make an app, and I would like to,
Yeah, maybe we can go to the... So, normally you have some... Yeah, also the app is an innovative part of our project. It enables to show creatinine concentrations in real time, and also has extra features. So it has a CreaView community, and it shows notifications based on what is happening with your kidney health. So the cartridge needs to be replaced every 2 weeks. This is built into the app, so you have to scan a QR code, and it loads in the new calibration curve for the new cartridge.
Okay, thank you. So, you still have time, or?
Perhaps we have a question from the audience.
We also worked a little bit with copper, and we found that when using something like transient voltages or EIS and applying a voltage to the deposited copper particles, we actually found some degradation which led to the lifting off of the copper. Did you guys find that at all?
No, I don't think so. Because it might also be that with like due respect, it might be because we are using like another polymer layer on top of it. So that might actually prevent, and the copper also is not a whole as copper layer, sorry. It's like copper kind of like nanoparticles kind of thing.
Yeah, we use this.
Yeah, so there are no like lift-off problems as such because they're kind of encapsulated by the polymer blend on top.
But what we found was not exactly left off, but detachment of the nanoparticles. So if there's a risk of detachment of the nanoparticles from the gold electrode, I mean, how do you ensure that there's a closed circuit then?
Because the circuit will still be complete because the gold layer is still underneath it.
But if the nanoparticles lift off and you have the insulating layer of the polymer?
But it's a blend layer, so PANI is still conductive. So it's not like a solid insulator and then a conductor. It's like a mix of this, which acts as an ionophore with the, let it be. So as in like it will let the ions still through and let the charges exchange. So it's not like a FET where you have like a insulator and then a conductor on top of it.
And was there any risk of interferences from other ions with the copper if it's a blend?
The interferences were not for the copper part, but there might be interferences from potassium ions and a couple of other ions, but that could be easily sorted by having 2 sensing chambers, which was something that we were planning to work on, but we didn't get enough time to do that. So you just basically have one sensor without the enzyme and one with everything else and the enzyme. So then you automatically cancel out the background that you will get because of the ions.
Thank you.
Yeah, thank you.
Any other questions from the audience? No? Okay, thank you.
Thank you.
Team test.
We are in the city of Eindhoven, the city of light. So it's not a surprise that the team from Eindhoven, Team Test, is also working on a light-based biosensor. Oh. So it may not seem like it, but this biosensor includes a light switch mechanism, and I'll talk through why that is. So the underlying phenomenon of our technique is FRET, First-Order Resonant Energy Transfer. And this is a transfer of a donor fluorophore to an acceptor fluorophore when they are close to each other without the emission of a photon. So let's visualize this. So we have this light, in our case a laser, and they are always exciting the donors. And when the acceptors come close to the donor, we see that the acceptors will receive this energy from the donor and they will emit wavelengths as well. If the distance is higher between the fluorophores, they will emit less. And what we want to measure is the FRET ratio. And if the acceptor emission is going up, the FRET ratio is also going up. So let's apply this to our molecular construct. So we start off with an antibody, labeled with these donors again. And attached to it is a protein in order to attach the DNA scaffold to the antibody. And what we see at the end of the DNA scaffold are 2 things. So we have this acceptor fluorophore, which is close to the donor, so it's emitting wavelengths. And that is because of creatinine acid. And creatinine acid is our analog to creatinine, and it has an affinity to the antibody. Therefore, in a default state, creatinine acid will attach to the antibody, and you already see that it's closed. But in the presence of creatinine, the switch will open. And that is because creatinine has a higher affinity to the antibody than creatinine acid. So creatinine acid will get displaced by creatinine, and you see that the distance between acceptor and donor will increase. So the FRET ratio will be lower. So we have a signal inversely proportional to the concentration of creatinine, which we can see here. So an increase of concentration of creatinine results in a decrease of FRET ratio. But what are the specifics of our molecular construct? So we've used the novelly discovered protein M, which attaches itself to the Fab fragment of the antibody. And our team have done mutagenesis on the protein M in order for it to attach DNA to it. And then we have the DNA scaffold. And it includes both single and double-strand DNA. It has been fully designed by our team, and it's designed in such a way that there is a good balance between stability, but also flexibility, so that the switch can open, but also close. And at the end of the DNA scaffold, we see this creatinine acid. fully synthesized by our team. And it's been made in such a way that the affinity is lower than that of creatine, so that the switch can close and open. So we have the construct. We immobilize it to the substrate, and we put it in a flow cell. And we want to analyze this flow cell. So we are putting it on a sample stage. And we know that in order for FRET to happen, we need light. So let there be light. This is the laser we are using. And what we then get are both the donor and the acceptor signals. And we want to measure them separately so that we can calculate the FRET ratio. So here you see them both. And we're using two filters. So first off, we're looking at the donor signal. So we are using the donor filter. Then we use our filter slide to move to the acceptor filter. And we get the acceptor signal. And these are both captured by the camera. And the camera can be used by the user through an interface. So the video is acquired. And then we are going to calculate the FRET ratio. So we are capturing the donor signal, then capturing the acceptor signal, calculating the FRET ratio, and then determining the concentration of creatinine. And that's what we want. So in conclusion, what we have created is a unique assay, fully created from scratch. And that is because we have used Protein M, we have designed the DNA scaffold fully, and we have synthesized creatinine acid. And it's worth noting that our method is easy generalizable. Swapping out the antibody and the analog, we can use our method for other biomarkers as well. And in our method, we are determining the creatinine concentration based on FRET, using our optical readout method. And by using this light-based biosensor, we hope to have made the City of Light proud. Thank you.
Yeah, thanks very much. On the FRET assay, how do you detect? Are you relying on detecting single antibodies?
We are using, as you can see, it's hard to see with the lighting, but we are grabbing a larger field of view, so looking at multiple events.
But at the single antibody
Yes.
level? Yeah, okay. And then how do you replace the creatine? So, I mean, do you have then a competition against...
Yes, we have this competition with creatinine acid. So in the default state, the creatinine acid attaches to the antibody.
No, go back.
Yeah.
Okay, so the creatine always replaces it. And how is this then reversible? How do you get rid of the creatine again if you want to have a continuous readout?
Yeah, so we are using a flow cell and we are flowing through a bigger volume than what was original in there. So all the creatinine that was in the flow cell will be like flushed out by adding a bigger volume.
Of what?
Of a new sample. So in the competition we added like there is room for 20 microliters in the flow cell. And in the competition we flow through 100 microliters of a new sample. So all the old creatinine which was in the flow cell will be flushed out. Or is that not what you mean?
Don't know. I'll give one.
I can just rephrase that maybe a little bit. These antibodies have very strong binding affinity, and you're already having something that is binding to it less. So I'm assuming that the binding with creatinine is very strong. And so when you flow the sample through the creatinine, there's no reason to unbind. And so that's the question. Will it unbind, and why, and how long does that take?
The exact biology specifics, that's for her. But we have tested the carryover effect, and we see that there is none. Well, it's not great. I cannot show you the graph, but the carryover effect is not significant.
Also, the antibody is quite low affinity for both creatinine and creatine acid. It's not that strong that it can't be attached anymore.
We picked the antibody based on we tried multiple antibodies and we picked them based on lower affinity, so a higher dissociation rate, so that it binds, but it does within a few short time dissociate.
Okay, so yeah, so let me come to the front.
So indeed, if the antibody has a too high affinity for the creatinine, it won't dissociate in time. But because we tried multiple antibodies and we tested where the carryover effect would be the lowest, and by choosing antibodies that don't have a too high affinity for both the creatinine and the creatinine acid, so the analog, it dissociates a lot easier. And then with the pressure of the flow coming through it, it does dissociate in time for the new sample to come in. So the old creatinine does flow out of the sample.
Okay, so I ask the next question. So I see a lot, and your team can be proud. Yeah, so a lot development on this biomolecular switch, and you also have in the results document, you characterize this very nicely. Yeah. But we have seen other teams, you know, they all talk about wearables and continuous monitoring and putting something on a patient. This is now a completely different thing you developed. You developed a desktop tool, right?
Yes.
So it sits on the desktop and you
our
test it.
business case is not based on a wearable.
Okay.
So maybe Danny can explain this a bit better.
Yeah, to not go into too much depth for the market potential, we are using it for the preservation of kidneys, for kidneys to be transplanted. So it's a desktop device, yes.
They are also continuous monitoring is needed?
Yes, they are.
Okay.
Well, currently no, but that's what we are bringing to the market.
Okay.
Yeah.
Okay. Good. What did the experts say? What did the experts say? Would it be good to have continuous monitoring?
Yeah, for
the
nephrologists we talked to, they thought it was a good idea.
Okay.
Thank you very much for your talk. Again, very impressive. I have a question regarding your actual essays you have done, because you showed the principle in detail. So how far have you been able to push it? Like, did you try to do any like calibration, concentration, and so on, or it stopped somewhere halfway? Because, you know, when I see the molecular construct, it's something what is unbelievably complex. Okay, I cannot imagine how you put it all together and made it work. But what about the assays?
Yes, so we tried different concentrations for the assay complex itself, and to see like what the effect was on the sensitivity of creatinine. And also we tried different methods to attach it in certain ways. We had some problems with clustering of the antibodies. So that's what we tried to solve, and we have been able to minimize it by improving the protocols and adding, I don't know if you know it, but tween 20, that's something that makes sure that the donors are not attaching to each other. So that's how we like try to improve the assay in such a way that we can measure in a certain sensitivity range.
Okay, thank you very much.
Yeah. And can I add something to that? Because the clustering did give some problems with the signal, so that's why we had to minimize it, because then the donors are very concentrated, of course. But next to adding tween 20 and magnesium to make sure that the DNA parts can attach together, we tried attaching all the DNA parts, because there are 4 in the scaffold, step by step, and then adding the protein and the antibody. But we have confirmed that all the separate parts, so the analog, the creatinine acid to the DNA, and also the protein to the DNA and the donors on the antibody, all those separate parts definitely work. We have tested them with gels and stuff like that. And then while assembling it, we eventually went over to assembling most of the scaffold first to make sure that that is very well hybridized, and attaching the protein M with the antibody first to prevent the clustering more.
So I just quickly shoot. Yeah, so your method you developed looks to me very sensitive. So it's much lower limit of detection than what we have seen from the other teams. Is that right? So the concentrations are in the sub-micromolar. Huh? So is this really needed, or would you need to dilute, or what is the practical application then later on? So I just see, you know, calibration curve with 4 data points. So I don't know, did you check for limit of detection and saturation of the sensor and so on?
At the when making the TRD document, there are 4 data points, but yeah, we have looked at higher concentrations, lower concentrations, and see what happened for the result. What we would like to do in the future is play around with the concentration of the construct so that we have better sensitivity results. But for now, the practical applicability is good enough for now.
being more sensitive is always good.
Yeah.
Short question. So you said fully creative from scratch. It was from your point. So which part do you exactly mean? Because this interesting essay has been published before you. And also I want to just a little bit explain about how you synthesize this complex structure. Thank you.
Yes, so the antibody was commercially bought, but in the paper, like I think you mean the Tom So paper where this was published in, the DNA scaffold is attached to the antibody. However, we chose to attach it to the protein M because we attach it with a cysteine-specific conjugation. And on the antibody, there are multiple cysteines. So you don't have complete control over where the scaffold will be. So in some of the assays, it will be on a different place than where you expect it. However, on the protein M, there's only one cysteine. So you know exactly where it is every time. Also, what we did, the protein M is already like a novel protein. But the cysteine that was on the protein was first on the top, so here. But that would mean that the scaffold would need to make like a 360-degree angle. So through two mutagenesis, we removed it here and placed the cysteine at the bottom. So the scaffold had a more wide range to make the angle.
And did you do these synthesizes yourself?
Yes. Yeah.
And also for the scaffolds, we decided ourselves which pieces we would need based on all the parts that we want on it. So we want the acceptor die on it, we want the analog on it, we want something to attach to the protein, and we need something to attach the biotin to immobilize it to the surface. So those are 4 parts. And we just played around a lot with sequences, and for every part we made sure that there was enough to hybridize so that it was stable in the attachment, but there was enough single-stranded as well for the flexibility, as Danny mentioned earlier. So with programs like the IDT oligo analyzer and NUPAC, we played around with the sequences to see which ones would attach nicely but still form the least secondary structure so that the hybridization that would take place would be nice. Thanks.
All right, I think given the time, please raise an applause for Team Test. All right. That was it, right? Yeah. All right, so those were the pitches. Now it's time for the partner market. Thank you for all being here, and and I would like also to thank the jury here for their hard work and their effort. So applause for the jury. If you have still some burning questions for the teams, now is the partner market, so you can ask them there. Have fun and get some fresh air if you like, because we've been here a while.
I forgot to copy it in the